Last week, we learned about some different kinds of energy, like kinetic energy, that's energy associated with motion, or gravitational energy, the energy associated with raising an object up in a gravitational field. Now, we will add on 3 new kinds of energy for our energy unit. Spring energy, thermal energy, which we had a prelude to last week, and chemical energy, which was also discussed briefly. But the real one that I want to focus on is spring energy. As a reminder, we have talked about springs before. Previously, you learned about Hooke's law, which told you about the spring force. Brand new marker. There we go. Hooke's law says that the force of a spring is equal to the spring constant times by how much we stretch it by, so K times delta X. And in this case, I'm just talking about the magnitude of the spring force, which is why I don't have a vector arrow above it and I don't have a negative in front of the actual equation, but it just says that the strength that a spring will pull on will depend on its spring constant and how much I deform the spring by delta X. We can store up energy in a spring also by displacing it from its equilibrium position. So here we have an object on a spring. If I pull that spring over to this point, there will be some energy stored up inside of the spring. And that spring energy equation is 1/2 Ks times delta X squared. So it depends on the spring constant of that spring and how much I pull that spring back. And the more that I pull it back, the more energy that I store up. And so here's our spring energy equation. This ends up being a work that is done on the spring. So let's take a look at if we can actually unpack that a little bit. Remember that work involves the force times the distance that I do that force over times cosine of theta. And we're going to take a look at this horizontal spring case where I have my smart car right here. I've got a spring on the end of it, and so we're going to think about how much energy is stored up in the spring when I deform it by stretching it out some distance. Right now this spring is stretched out and it's got some energy stored up in it, and I can retrieve that energy and turn it into different kinds of energy just like we did with gravitational and kinetic energy. So in this example, I got spring energy in the beginning, I let go of it, and it turns into kinetic energy to get this car moving. Let's take a quick look at what we can actually gather in terms of data for this work done by a spring. Remember that if I have a work being done, that means that I have a force acting over a distance, and in this case I will be pulling directly to the left and the spring force will be in the opposite direction, so effectively this cosine of theta goes to 1 because my theta is 0 in this case. So once again, our work is just force times distance. So here on my plot, I have force and distance, and we're going to see what we get when I end up pulling on this spring. I'll start recording. I'm going to move the car about 1/2 meter. There we go. And I'll stop recording, and let's auto scale this so we can see what kind of graph we get. Right here we have a linearly increasing positive trend between force and position. You can just sit with this for a sec, and this should make sense. We talked about Hooke's law. The spring force is equal to K times delta X. And in this case, that means that as I stretch it out more, as my position increases, my force should also increase. And from this graph, we can somehow get the spring constant. Maybe I'll allow you to think about how we would get that from this graph. So let's take a look at this relationship that we have. Here I have force on the vertical axis, and I have distance on the horizontal axis. That force was in newtons, the distance was in meters, and right here we call it position, but since I started at 0 position, whatever my change in position is will be the distance over which this force acts, and we ended up getting a linear relationship between the force and the distance. Now, if I wanted to calculate the work done, I would just take my force and multiply it by my distance. That would work if this force was constant. I could just take whatever force it was and multiply it by how far I pulled it. But since my force is changing throughout this motion, we kind of need to take an average of the total force. But a shortcut for determining the work is realizing that I just need to figure out the area under the curve for my force versus distance graph. So here we could say the area under force versus distance graph. What that will do is it will give us the work. Gives the work done by the spring. So let's take a look at the actual work done by the spring. If we think about the force and the distance. Great. New markers. We're going to calculate the work done by this spring, and that'll give us the energy. I told us that the area under this force versus displacement graph would give us the work, and the area of that shape, it's a triangle, so the area is 1/2 base times height. But now instead of just thinking geometrically base times height, we can think about what our actual base is for this. The base of this triangle is the distance d. The height of this triangle is the force that was exerted by the spring. Force of the spring. And so we can continue to derive this formula by saying 1/2. This time, instead of distance, I'm going to call it delta x. It's the change in my position that I got from Capstone. And my spring force, I should be able to substitute in Hooke's law, which is written in blue right there, that says the spring constant times delta x, and that is my spring force. I can simplify this expression a little bit and write 1/2. I'm going to bring my spring constant to the front, and I have a delta x times a delta x left over, and that ends up equaling delta x squared. We calculated a work here done by the spring, but you know work and energy are two sides of the same coin, so really this is just the spring energy equation. So the shortcut for this work versus, or force versus displacement graph is the area underneath it will give you your work. That was not covered in the PowerPoint, so that's a slightly new idea. Let's take a look at what some of the other content was, and then we'll jump into our experiment for the day. We also spoke about thermal energy. You saw this a little bit last week, but thermal energy will only exist when friction is present, or when there's air drag or something like that. So in reality, we always have a little bit of friction. Objects rub up against each other and generate heat. And one of the keys to realize about thermal energy is that once you have thermal energy in that bin in your energy bar chart, it will never come back out. There's no way to get the heat energy that was given off to the environment back into your system. So it is not recoverable in your energy bar chart. If you have one block in thermal energy, for the rest of the entire graph, there will always be at least one. And then maybe it'll keep growing. So sort of like this energy skate park where we had our skater having gravitational energy and then kinetic energy. When we added in friction, they slowly came to a stop and a zero height. And you'll recall that that thermal energy bar got bigger and bigger and bigger until the whole total was thermal energy, and there was no way to get it back into some other kind of energy. Chemical energy is another type of energy that we briefly spoke about. What you need to know, your shortcut for chemical energy, is that anytime there's a person metabolizing some food or a chemical reaction like combustion happening, or some type of physiological process like photosynthesis in a plant, that's when you'll end up having chemical energy showing up. It's the energy that's stored up in bonds, so when we're breaking bonds or making bonds, there will be a change in chemical energy. And now Energy conservation still holds true, but instead of just having kinetic and gravitational energy like you had in the past, you'll need to think about all of the different kinds of energy, and our experiment that we're doing today does have all of the energies in it. So we're going to think about that in just a sec when we jump into our lab. Just want to briefly touch on the last 2 points that might show up in Expert TA. There's an idea called efficiency, which is basically how much energy do you get out from the amount of energy that you put in. It's a unitless number because we have joules over joules. And the one that I really wanted to make sure I spoke about was power. Power has the equation of energy divided by time. It's a rate at which energy is expended. So much like we had velocity being the rate at which position changes with respect to time, now we have the rate at which energy changes with respect to time, and that's called power. It's measured in a unit called a watt, which is equivalent to a joule per second. So most light bulbs in your house are probably about 60 watts. That means they consume 60 joules every second. Finally, our last diagrammatic model for energy is called a system schema, and this should feel a lot like an interaction diagram. We're going to gain some practice with that in the practice problems on Friday, but it's basically an expanded interaction diagram that still has all of the objects present. The forces will be written in shorthand notation rather than agent-object notation, and what's really useful about system schemas is it allows you to choose a variety of objects to include in your system. Whether you want it to be open or closed will depend on how you draw this dotted line, whereas in the interaction diagrams we usually only looked at one object. Now we can open it up or change it around and think about if there are external forces coming in or out of our system, which will change around the energy conservation statement. More on that on Friday. All right. So we have an experiment where you can see each group has an inclined plane right here. You all have your own smart cars and some masses to put on them. Before we start experimentally, let me just show you what we're going to do for our lab. I'm going to hook up this spring to the top hook right there. And we are going to think about the energy of this system as it goes down the ramp. So first we're going to start off with this car right here. You can think about what kinds of energy it has. I'm going to load it up with a little bit of mass to make it a little more interesting. And soon I'm going to have you draw some energies, but let's just watch the motion first. It starts out up here. I'm going to drop it, and then I'm going to catch it at the bottom. Let's watch it 2 more times. Think about what the spring is doing, the car, think about the height. Here we go. 3, 2, 1. One more. I don't want it to oscillate or bounce up and down. I just want to think about it at its first point, the midpoint, and the last point. Okay? And what I want you to do on your whiteboard right now is draw me up some system state diagrams and energy bar charts. So at the very top of your whiteboard, draw a big rectangle. There. 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 And in this rectangle, I want to think about what the energy will be doing at the beginning, the middle, and the end of the motion. So we need to split this into 3 different panels. 1, 2, 3. Each of these panels will have a track. Your track should be inclined according to how you're looking at it at your table, so I'll draw it from your perspective. There's my inclined track. And these are going to be system state diagrams. For when our car is at the top, the middle, and the bottom. And then we're going to draw up energy bar charts to go along with each of those stages. So I would want some axes there, there, and there. So that will be our energy bar charts that go along with this. First, let's talk about the system state diagrams. On your system state diagram, you must draw 3 objects. You must draw the car. You must draw the spring. And you must draw the track. And remember in your system state diagrams that each of these objects needs to have the variables that will tell you about the energy. So for the car, you'll need to say something about its speed. You'll need to display where V shows up. For the spring, you will need to put something about the stretch distance. We call that delta X in our system state diagrams and in our equations. And the something about where the car is on the track that we will need to list is the height, H. So in each of your system state diagrams, you need to draw the object, which is the red, and the variable, which is the green. I'll allow you to think about that, and I'm sure you'll get some different answers. Let's just brainstorm for a quick sec. Which types of energies will be present throughout the motion of this entire process? Can anybody list for me one type of energy that they think will show up, Chelsea?
Gravitational.
Gravitational energy will definitely show up because it's changing its height. What's another one? Ari? Kinetic energy because it's changing its speed. What's another one, Andrew?
Spring energy.
Spring energy because we have a spring in there and it's stretching out. There should be one more. Mohammed?
Friction.
Friction, we call that what kind?
Thermal energy.
Thermal energy. Thank you very much. Very good. So we have ETH is what we call that one. Where in reality, the wheels are rubbing up against the track, and therefore there should definitely be some thermal energy as well. And now this is our warm-up activity. So let's shake off the rust and let's see what we got. 10 or 15 minutes to draw these out and remind yourselves. Nate and I will be rotating to answer any questions, but just to start off, let's see if you can be resourceful and try to think about this situation. Go. Okay, can I please have your attention? Let's talk about what we were expecting to see for our system state diagram. We need to have a spring in there all the time. So I'm going to put a spring and I'm going to go 1, 2, 3, 4, 5. It's really compressed right there. And so I'm going to draw my car as a little dot. If you drew it as a car, that's even better artistry work. In the middle, our spring is going to stretch out a bit. 1, 2, 3, 4, 5. And we'll be at about the halfway point. And then once we're at the bottom, we'll have 1, 2, 3, 4, 5, and it'll be all the way down there. So we've drawn all of our objects, the car, the spring, and the track have been shown. Now let's think about what those variables are and where they show up. My speed in the beginning should be equal to 0. So I would put that as an arrow, but it doesn't have any, so it would be like a 0 length arrow. In the middle, it is moving down the track, so I'll make sure I include an arrow there to say the speed, and I like to list these, and we don't know exactly how fast it'll be moving, but we know it'll be moving pretty fast in the midpoint. It's about as fast as it gets, so I'm just going to call it fast for now. In the end, our car, once again, is not moving just for a moment, a brief moment in time, so the velocity should be 0. Our height will show up, because if I call the very bottom my reference point of h equals 0, the height should be an arrow that extends upward from there, so there's the height. And I'm just going to go ahead and call that h the initial height, h initial. You could have called it 10 centimeters or something like that. And then h shows up right here in that spot. It's about half the height, so I'm going to say h equals 1/2 the initial height that it was at. And then at the very end, our height ended up equaling 0. We're going to set our reference point to be that lowest point that it gets to. That's our 0 point. And then we have a new variable that we have to include called the stretch distance, delta x. And initially, the spring is not stretched at all, so delta x equals 0. It started out right here, and it's stretched down to about the midpoint, so my stretch distance will show up on this diagram right there. There's my delta x. And then that delta x gets even bigger at the very end. Delta x should be all the way from where it started to where it ended, and your system state diagram is now complete. We can use these variables to help us say something about the energy bar charts. Most of you have a pretty good idea, but maybe you'll see a little something that is kind of helpful for you in the future. I don't know exactly how many bars to include. I see some people have 5. I see some people have 4. I see some people have 6. So I'm just going to show you how I would think about this one. Initially, we have 0 speed. That means kinetic energy is going to be at 0. We have 0 stretch. That means our spring energy is going to be at 0. The car hasn't rubbed up against the track at all in the beginning, so the thermal energy is going to be 0. That means all of the energy has to be gravitational energy, so I'm just going to put a big bar there. There's my gravitational energy, and I don't know exactly how many bars make sense yet, so I'm going to wait to separate it out into a certain amount of blocks. Let's think about the next example. Here, I go down in height. My gravitational energy will go down, and once we're halfway across the track, our height should be at about half the height. So however tall I made that first bar, I'm going to make this one about half as tall. Still don't know how many blocks to put in, but I know it needs to be about half the height. It's going to have some kinetic energy because it's got a velocity, so I'm just going to put a block in there. And it's stretching out a little bit. So I'm going to put a little bit of spring energy in there. And it has rubbed up against the track a little bit, so I'm going to put 1 block of thermal energy in there. Okay, let's look at the last one before I separate out this bar into several blocks. The last one has 0 velocity. That means my kinetic energy is 0. The last one has 0 height. That means my gravitational energy went to 0. The last one definitely rubbed up against the track a little bit more, so I should certainly have more thermal energy. So I'm just going to put 2 blocks in there. 1, 2. And now you will find that the greatest common factor for this separation of blocks should end up being about 6. That means that if I had 2 blocks here, everything else that was initially in the system should be spring energy. And now, if you look at this, it makes sense that I should separate this into being 4 total blocks for spring, 2 in thermal, 1, 2, 3, 4, 5, and 6 for my gravitational energy. And so this one might make sense to separate into 1, 2, 3, 4, 5, and 6. To me, 6 bars makes the most sense. This is completely qualitative. This is a conceptual idea telling you which kinds of energies are present. It is not a direct quantitative representation of the numerical value of joules that are in each bin. But we know how they all need to be distributed roughly. All right, so I'm sure that you can look at your graphs or your system state diagrams and your bar charts and see that maybe you wrote yours slightly differently than me, but this would be an ideal representation that you could use. So please make sure that every time you do a system state diagram, you do show where the variables show up, you do list them as clearly as you can numerically, and that your bar charts end up matching up nicely with that. Now what we're going to do is we are going to think about the energies in a more quantitative sense. And we're going to plot a graph that has energy on the vertical axis and time on the horizontal axis. So we're going to look at how our energy in joules will change versus time in seconds. And I'm going to want you to list each of the different types of energy that could be in there. So we got EG. I'm going to make that blue because the Earth is blue, and without Earth we wouldn't have gravity or gravitational energy. I'm going to need you to plot kinetic energy on there. We have our spring energy as well in the system at different points in time. I will plot thermal energy as red because it's red hot. And also, there should be one other kind of energy that I want to make sure shows up on this, and I'm going to make that the total energy, E total. What should be true about the total energy for this closed system, Tyler?
Never changes.
It should never change. It should be a constant value. And it should be bigger than all of the other ones. All the other ones need to add up to equal the total. So at the very top of your graph, you will have a line there for the total energy. And all of the other energies that we plot throughout time have to add up to equal that total. So, you know, there will be some lines. We're going to draw a line graph for each of these to think about how the energies change over time. So you might have one line going down, or some lines going up, or maybe they go up and then down, and you'll need to think about how the qualitative energy bar chart will match up with the quantitative energy versus time graph that we're going to end up making at the end of class today. So can you please take your whiteboards down and let's make a prediction. Think about what all of the energies would look like as time evolves.
My goodness.
Let's see if you can get a good idea. Just think about if they should increase or decrease or change around. All right, so everybody has a rough guess of what they are expecting. Maybe your guess is reasonable or not. Let's just talk about what we're expecting to see when we eventually get this graph. You can match up the energy bar charts with the energy versus time graph that we're going to make. We started off with only gravitational energy. So that's the one I'm going to start with. And the total amount of energy, I hate this marker. I won't use my new ones. All right, we started off with all gravitational energy. So in the beginning, the total should be equal to the gravitational energy. Right here, the only amount of energy that I should have in the start is gravitational energy. What that says is that the energy total in the beginning should be equal to all just gravitational energy. If I was to write out energy conservation, that'd be all that I had for the total in the beginning. And its gravitational energy is going down over time. So I'm going to say that it goes down, and it should eventually end at 0. So I'm just going to make the guess and say it's going to be a linear decrease. Maybe it'll actually be, I don't know, quadratic or something, but right now we're just kind of predicting, and so all we can say is that it started at a maximal value and ended at 0. Now, let's think about the kinetic energy next. The kinetic energy started at 0. It went up to some number, and then it went back down to 0. So I need to make sure that it starts off at 0, ending at 0, and makes it to some higher value in the middle. So that could be what our kinetic energy looks like. I don't know, maybe it looks like a triangle, maybe it looks like a kind of weird S shape, or maybe it looks like a perfect parabola like we've drawn here, but all that we really know for sure is that it's going to go up and then go back down. The spring energy starts off as 0, goes up, and then continues to go up. And so we're going to need to start at 0, going up, but it's not quite going to reach the total. Not all of the energy will end up being the spring. So we need to maybe put it about, I'm just going to say, 2/3 of the way there. So there's my spring energy. And then the one that we have left over is the thermal energy, and we knew that it started at 0, it got a little bit bigger, and then it got even bigger. And one other thing that we can say for sure is that in the end we have no gravitational, no kinetic, we do have spring energy, and the only thing that's left is going to be thermal energy. So whatever the difference is between the total and the spring energy has to be given up as thermal energy. So I'm going to put a dot right there, and I'm going to say the thermal energy goes up over time as it rubs up against the track more. And so this is roughly what we're expecting to see in the graph that we get in the end. You all have a rough guess, and it should be somewhere in the ballpark of this. I think everybody's sort of got it down. And we're going to try to end up making this graph in Excel. But to make this graph in Excel, we're going to have to do a bunch of calculations. We're going to have to think about what variables will be present in these different equations for the different types of energy. So I've listed our different energies right here. I would like if we had a 2-minute discussion amongst your group. Just think about what would I plug into Excel, what kind of numbers would I multiply together, what's the formula for kinetic, spring, gravitational, thermal energy, and total energy. If I was to make a column of data with those numbers, what variables would I need? Okay, so quick discussion, and then maybe I'll call on some individuals to help me out. Go. Who thinks they know the formula for kinetic energy? Anybody who's looking for some participation points? If you made it a goal to speak out more in class, this might be a good time to do that. Haley?
Half mv squared.
That's correct. That's the formula for kinetic energy. 1/2 mv squared. So if we have all those numbers, we could plug them into Excel and get a value for it. Excellent. Who thinks that they know the spring energy? Carolyn?
1/2 ks delta x squared.
That's correct. 1/2 the spring constant times the stretch distance squared. Exactly. So as long as we know our spring constant and how much our position changed by, then we should be able to calculate the spring constant. And I'd just like to make a quick note. We are calling this delta x right now, but really that stretch distance will be along the diagonal distance. So when we say delta x, I'm not just talking about left and right in this case. I'm talking about the stretch distance along the diagonal. So just for a sec, assign that delta x as a diagonal length, okay? That'll be the position that our smart car changes by. So wherever it started and wherever it ended, we should be able to read out that position as our delta x. Now the next ones will end up being more complicated, but I still know that you can do this. Who's got an idea for EG? Autumn?
Mass times gravity times height.
Good. M times G times H. But let's think about this from an experimental perspective for a sec. This smart car, it measures the change in position by how its wheels spin. And so it'll definitely tell me the diagonal distance, but it cannot read out the height to me specifically. So when I'm doing this experiment, we need to figure out a way in Excel to calculate the height that this thing changes by. Does anybody have any ideas of how we might be able to figure out the change in height? Lillian?
Use trigonometry.
We can use trigonometry, that's exactly right. So if we have a track right here, and our delta x, we started here and we ended here, the smart car can tell us what delta x is. It will tell us the change in position, but not that blue. The change in height from that point to that point should look something like this. And Lillian has told us that we can use trigonometry to figure this out. So if we know what angle theta our track is at, there should be a way that we can set this up to solve for the height. Because we'll know delta x. We got that. We got that. We don't have this. So briefly turn to your neighbor and just think, which trig function would I use? How would I set it up? Discuss. Go. Okay, that's our 30-second discussion period. Which trig function do we think we'll need to use, Mara?
It'd be sine of theta.
It would be the sine of theta, and I'll just get caught up with you. Sine theta we usually say is the opposite over the hypotenuse. In this case, delta x is our hypotenuse, and h is our opposite. We're trying to solve for h, so we can write h equals, and we'll bring that hypotenuse to the other side. To just get h alone, we should be able to use a formula that says delta x times sine theta. That should tell us the height of the triangle. So Autumn got us started by saying m times g times h, but really when we go into Microsoft Excel, we'll need to do m times g times our position times our sine theta. Now that one's a little tricky, and the more you gain practice in physics, the more you'll be able to see this ahead of time. but I'm not sure that would have immediately jumped out to you in this experiment. Okay, let's keep discussing, and actually, the one that I want to talk about next is E total. Before we go to ETH, there's a reason why, but can anybody think about how we would figure out the total amount of energy in our system? Zoe?
The initial gravitational energy.
That's a very insightful comment, and that is correct. That's the one that I'm looking for. Can anyone think of another way to calculate total energy? Lillian?
You were to add up all of the energies.
Right, so that I would have accepted two answers here. We're going to end up going with that one, but the total energy should just be EK plus ES plus EG plus ETH. But we don't have ETH yet. So we don't want to just add up all of the different pieces of energy and say that's our total. Actually, a much more useful way of figuring out what the total is just saying what we wrote right here. The total initial energy should all be gravitational at the start. And if we know what gravitational energy is there, the total should stay the same throughout. So that is just going to be what sets our total energy. We will need to figure out what EG in the beginning was. And we'll just set that equal to E total the whole time. Now, given all of these other variables, can anyone think of how we would calculate the thermal energy? Andrew?
The total energy minus all the other energies.
Right. So here we will have E total minus EK minus ES minus EG, and that should be what we can use to calculate our thermal energy. We're thinking ahead of time about what numbers we'll need before we go into Microsoft Excel. Speaking of which numbers we'll need, now that we have the formulas, let's think about which variables would be good to measure ahead of time before we actually start the experiment. I'm going to look at kinetic energy first. CAPSTONE can give us a lot of these variables. It'll give us position, it'll give us velocity, and we could get force if we wanted, we could get a lot of stuff, but it cannot tell us one of these variables, Tyler.
Mass.
It cannot tell us the mass of our car. So we're going to need to list that. The mass of our car will definitely be a number that we need before we get started with the experiment. And we're going to measure that in just a sec. But I want everybody to get your car with the masses that are already on it. And I just want you to give it a test run. We're not even collecting data. Start with it at the top. Be careful. Don't let it slip off your spring or anything like that. Let it go. And observe if you have a nice range of motion. I don't want it to just go a little distance. I want it to go like at least a meter or so. So get it ready. Do you feel like that's enough? We might end up giving you a little bit more. Let it go, and hopefully it goes at least a full meter. And so now everybody should have chosen the amount of mass that they want to put on our car. Let's scale it out. Let's go put this on the scale and figure out what the mass of your car is, including the weights on it. And don't forget, if you overload, you might need to do 2 separate measurements. The standard units for mass is kilograms, so I don't want to see anybody ever displaying your mass in grams, right? Kilograms is the standard. You'll never get the answer wrong if you keep it in kilograms. So now let's keep looking through these numbers. We got our mass. Let's go look at the next formula. Our delta X will be given to us by CAPSTONE. But KS, we don't know yet. I want you to fill in on your board, put KS equals, and we're going to leave it blank for a sec. I'll show you a shortcut for figuring it out. If you were to try to figure out your spring constant, there's a couple of ways that you can do it. We briefly did this as a short activity in class after the Wait, Don't Tell Me lab. But I had a little spring on a post, and I had a force sensor, and I pulled it at a certain distance, like 10 centimeters, and I read out the force, and I used that to back calculate my spring constant. Another way that people would do it is you would hang the spring vertically, put some mass on it so it stretches out, you measure how much its displacement is, and you set the spring force equal to the gravitational force, and you can figure out your spring constant that way. But there's an even quicker way that we're going to go over in just a little bit once we get into CAPSTONE. So we got mass, we got spring constant. Let's look at our next. We still already have mass, we know G, we'll know the position. But to do these calculations, we will need theta as well. That means we need to know the inclination of your track, the angle of inclination. Can anyone think of a way that we could figure out the angle of inclination? Lillian?
Read the angle on the track.
You could read the angle off the protractor because all of you have been given a protractor. Another way is you could use trigonometry. You could measure one leg of the triangle and another leg of the triangle and then back calculate it out. But you have a protractor here, so everybody take a look at your protractor and figure out what angle you're at. I'm at 10 degrees, and put it on your board. Now we look through our variables. We got everything that we're going to need to calculate all of the other ones. Once we have our spring constant, we will be good. So it's time to wake up your computer, and there should be one person who hasn't actually played on the computer yet in this group, right? I think we had 2 computer days, so now it's someone else's turn. Get on in there. Please open up CAPSTONE. Please turn on your smart car and get it connected up by going to the sensor data and then connecting. Okay, let's talk about this a little bit. First, I need you to go to hardware setup right there and go to your smart car position sensor. Go to the settings and make sure that you have change sign selected in your settings. Once you do that, you can hit OK and back out. You can now hit hardware setup to get this panel out of the way. And we are going to end up collecting 3 different points of data. So on your horizontal axis, select time. You need to make sure that the horizontal axis is in time by selecting that measurement there. And then I want you to add 2 more plot areas by using the Add New Plot area. So click that twice so you have 3 total plots. You should have 1, 2, 3 plots. On our first one, I want for us to have position. So select the vertical axis and go to Smart Car Position Sensor and hit position. On our second plot, I want for us to have velocity. Smart Car Position Sensor and hit velocity. On our last plot, click the select measurement and go to force from the Smart Car Force Sensor. These will all be needed for us to calculate out any of the other relevant variables. I'm just going to clean this up a bit so that you can see what's going on. Okay. Everyone should have 3 graphs of position versus time, velocity versus time, and force versus time. We need to do a little bit more equipment setup first. So experimentalists, please grab your smart car and put it at the bottom bumper so that the hook is facing up and it's not moving. Put it at the bottom bumper, not the top. Let it rest there. And we are going to zero this out with your mass on it. So what I need the computer people to do is go to the very bottom, select position sensor, smart car position sensor, and hit that 0 button right over there that says 0 sensor now. Nobody should be touching it while it's being zeroed. Once you hit the 0 button, you're good. So you should be on smart car position sensor and you should hit that 0. Next, you should go to the smart car force sensor down at the bottom and also hit the 0 button. This tells it that nothing is touching that hook right now. Zero your smart car force sensor. And then the last step is to click this bottom thing and go to common rate. Click on the bottom where it says smart car force sensor and go to common rate. And this says that it's going to collect all of these in the same rate at the same time. It's going to collect position, velocity, and force. Make sure at the bottom that you click common rate. Good. I believe that we are all set up. So first, one thing that we can do is I'm just going to hit record real quick and let it chill for a sec. And everybody should do this really quick just to make sure that you're getting 0, 0, and 0. 1 or 2 seconds of data. Let's just make sure you're reading roughly 0. Good. Alright, that's a nice little sanity check. I'm going to go to delete last run, just to delete that and get it out of the way. And now I would like for me to show you how to do it, and then I'll allow you to take the data. So the first step is to get this thing on the track. You want your spring to not be stretched at all, but to be in contact with the hook. Then we are going to record and let it sit there for like half a second or a second. Then let go of it and catch it right at the bottom before it starts finding its way back up, and maybe even just let it run for a little bit longer to make sure that we collect a full range of data. And what everybody needs to end up having is a position graph that starts at 0 and increases, a velocity graph that starts at 0, goes up and then down in a nice parabolic shape, and a force that goes up from 0 and then flattens out. So it's our turn to collect these. Please call Nate over to make sure that your data is clean enough to run once you actually have it collected, and then we'll pause at that. Okay, everyone. So we are going to be on our break soon, but we just have a little bit more work to do before we get set up. First off, computer people, can you please hit scale axes to show all data? Maybe you already did that. That's nice. And the next thing that I want to do is I want to look more closely at where you specifically did the experiment. I want to look at this time window. So identify for me, realistically, what was the initial time that you let it go at? And what is the final time where you are willing to cut your data off? And just over-select like a little bit. So for me, mine started a little bit before 4. I'm going to select the data from 3.6 all the way to maybe 5.6. So determine by looking at it what you think would make sense. So let's, I want to show you something. We can click on this time down at the bottom now, and I just want to kind of zoom in on this window so I can see more closely what happened. So right-click your numbers at the bottom, go to Axis Properties, go to Axis Scaling, and now set your minimum and max value to what your times were. So mine is going to be 3.6 and 5.6. If you missed some of those details on how to get there, please raise your hand. Nate knows how to do that. All right, so the next thing that we're going to do is we are going to add a new page. Please go up to Add Page. And now that we have a new page here, I want you to select that first table and graph. Add page, and you need a table and a graph. And now we have a table and a graph that we're going to get our numbers on soon. First, let's look at the graph. And what I want to put on this graph, in your vertical axis, can we put force there? So click on it and get force from your smart car force sensor. And on your horizontal axis, I want position. This graph should remind you of a graph that we've seen today. Why do you think that this is useful? Which object are we talking about here? Lillian?
For finding the spring constant.
That's correct. We're talking about the spring right now. It's feeling a spring force and it gets bigger over a distance. How would we find the spring constant from this? Lillian?
The slope.
It's the slope. The slope of this force versus position graph will give you the spring constant, because remember, Hooke's law, the spring force equation, in terms of just its magnitude, has a Ks times delta x. If this is my independent variable and this is my dependent variable, the slope should be whatever this coefficient is in front of the independent variable. So we need to add a linear trend line. We can do that in CAPSTONE by going up to this apply selected curve fit using the little arrow and selecting linear. Write down your spring constant on your board. It should be the slope M. The next thing that we need to do is we need to go into our table, and we're about to copy some values to Excel. The first thing that I want you to do is in your table, click this Insert Empty Column. We need one more column, so please click that Insert Empty Column button once, such that you have 3 columns now. Now, for our first column of data, I want time. So click on it, select measurement, go to time. For my second column, I want position. And for my third column, I want velocity. Okay, so you should have a graph that has time, position, and velocity. You can kind of just scroll through and take a look at what happened. You know, some points it was moving, some points it wasn't moving. Please scroll through your data table until you see the starting time that you had. Mine was 3.6. Go to 3.6 and click on that first one at 3.6. That's your time. And now we need to highlight all of the data from where you initially started your time to where you ended the experiment. Mine was 3.6 to 5.6, so I'm going to click on it, hold the click button, and drag all the way down until I get to my end point. There's 5.6.
I changed it to 1 to 3.6.
Everyone should have their data selected and highlighted. What I need you to do is right-click it and go to Copy Values. Right-click and copy all of those values. Go ahead and open up Microsoft Excel. Get a blank workbook and paste it in. We have the data in Excel. The final thing that I need you to do before we go on break is I need you to save this and email it to everyone, including yourself, and then pull out your laptop because I want everybody to do the Excel together today. Once you have this on your laptop screen, you may go on break. Let's do a little bit of housekeeping on our Excel sheet. We're going to do a bunch of Microsoft Excel. So at the very top, please change our column headers. Right now it says time, S, auto, position, velocity. Let's change that time and let's just call it T in seconds. Let's change our position to X in meters. Let's change our velocity to V in meters per second. If you end up falling behind, please immediately call Nate over because there is going to be a lot that we're doing, and I'm sure there will be 22 people who will be caught up and 2 people who fall behind, so please raise your hand when you fall behind. I'm also going to just bold this so that we can kind of keep track of where the top of this is, and also I would like it if we hit Control A or Command A to just grab everything, grab all of your numbers real quick. You'll see right now that we are in scientific notation, and that's kind of not a nice way to look at a spreadsheet. So once you have all of your data selected by using the Select All menu, please go to Home, go up to Number Format, right here. In the middle it says Scientific right now. I want you to hit that drop down and just go to Number. Now it's time to start calculating some of these variables. So what I want our next one to calculate is going to be h. Let's look at how much our height of our car changes by. And we had a formula that we talked about for h. Really, h was the position times a trig function called sine of theta. So we're going to end up typing that in as a formula. We're going to start off with an equal sign saying that we're going to do some kind of calculation. Go ahead and grab your position number by just clicking on that cell right next to it. So you should click B2. Let's put an asterisk up there for multiplication. SIN for sine. And we can't just actually put our angle theta in there directly because Microsoft Excel uses radians, actually. So what I need to type is RAD, and you should be able to double click this little function down here that says it converts degrees to radians. And then you can put your angle in there as 10 degrees and close it off with 2 parentheses. So your formula right in here should be this. Definitely pay attention to, Nate, in case the group needs to be caught up. You're going to have to do some of that. So it's the position times the sine in radians of your angle. Hit enter, and then you want this formula, it should be at 0 height. You should drag this all the way through by clicking on this little square in the bottom right and dragging it all the way down to the end of your data. Okay? So we should have a height. All of these should be in number. So I'm not sure why mine wasn't. But go ahead and grab onto that data as well and make sure that all of your data comes out in a number format. And so you should roughly have an H value that looks like what I have. Please call Nate over if you fall behind. It's perfectly okay to get individual help. Your height right now starts here and then it seems to be getting bigger over time. We'll talk about that in a bit. All right, we've calculated our height. Now actually, to make this a little bit faster, we're going to copy over this time column and put it in column E. So please grab onto the whole first column by clicking the A up at the top. Click the A up at the top, and that should grab onto all of this data. And then copy it, either by right-clicking or Control-C, Command-C for Mac folks. Click on column E, and then paste. I'm just taking my numbers from A and putting them where E is. You should have your numbers copied over from A and placed into E. Also, I got a lot of feedback on the feedback survey saying that I go too quickly through the computer portion, so I'm really attempting to pump the brakes a lot. I'm sure for some of you it will feel a little slow, but I don't want anyone individually to be left behind. So, now we're going to start doing some extra calculations next to these. We're going to calculate in the order that you see there, except we're going to switch total and thermal. So that means I want EK right here in joules. I want ES right here in the next one. I want EG in the next one. I want E total in joules right there. And I want E thermal in joules at the very end. So please match up your column headers to mine. And it sounds like you've gotten it. Okay, so now let's try calculating our kinetic energy. What we'll do here is we will type in the formula that's in green. So we need to somehow turn 1/2 mv squared into language that Excel can hear about and understand. So let's type an equal sign. 1/2 is 0.5. Make sure you leave an asterisk for your mass. My mass is 1.018, but your mass should be different than mine, so just type that number in exactly. And then you should have an asterisk, your velocity. So go click your velocity value, which will be in column or cell C2, and raise it to the second power by using a caret 2. That says 1/2 m times v squared. And hit enter. Leave this open for anybody who still needs it. 1/2 m times v squared. And last time I had you drag this through by using the little square at the bottom. I'll show you a shortcut. You can just double click that square. If you double click that square, it'll fill it all in for you. Even though I wish this was a Microsoft Excel course, this is not meant to be an Excel course, so I'm not going to give you the exact details on why we're doing exactly what we're doing. If you want to learn how to program or you learn Microsoft Excel, you can take my sports science class, where I quite literally teach it from the very beginning, how to code and program from stage 0. All right. Nate, question? Please keep raising your hand. Put this kid to work. This is good. For our spring energy, Most people should have your kinetic energy all the way through.
Yeah, so you're gonna do your velocity.
It's because you're on a tablet. I will come help you in a sec, okay? Just do the first.
Use control.
Yeah, okay. Anyways, in your spring energy, you should have an equal sign. We're going to type in this exact formula. 1/2 K x squared. So we type 0.5 times our spring constant. You should have figured out, you should have it written on your board somewhere, minus 4.94. We just put that number in exactly. 4.94 times your position, it should be in V2, and you square that. Enter.
Square's carrot, right?
Square is caret, that's right. Caret 2. 0.5 times your spring constant times position squared. And you will drag and drop this through just like we did for the last one. Alright, this looks pretty good. There's going to be something that I'm going to correct in a sec. So if you know what's wrong with the sheet, don't give it away quite yet. It's time to calculate our gravitational energy. Let's type an equal sign. We need m times g times h, and we already have the value for h calculated right here. So what we're going to do is we're going to take our mass, 1.018, times g is 9.8, times our height. You should have m times g times h in this gravitational section. And you hit enter, and we drag and drop this through. K, S, and G? Okay, so let's do a little bit of a sanity check right now. Before I go any farther, usually it's a good idea to double check your numbers to see if they make sense. That's just good in physics class in general. I have my kinetic energy starting at 0 and eventually going up. Is that right? That should feel good. Kinetic energy is the green line. It started at 0 and started going up. ES starts at 0 and eventually gets bigger. My orange line started at 0 and started getting bigger. EG starts at 0 and gets bigger. Oh, wait.
Oh wait.
Is it supposed to do that?
You didn't do
Like,
So, there's actually a small problem in the way that we calculated out our gravitational energy. And it's in this column H. Realistically, this column H, you started at a high height, right? And then you went down. But right now we have H saying 0 going up. Aha! So, let me show you what we actually need to correct our gravitational energy as. Please click back into your first cell of H2. You can double click to open up that formula again. Right now I have m times g times h, but there's a problem with our h. Alarm bell should have gone off in your mind saying that that's not quite right. So what I want you to do first off is put some parentheses around the D2. So be very careful. Don't use arrow keys when you're doing this. You have to use your cursor. You have to click around. And then get back to the front of D2 and we're going to add something. What we're going to add here is I actually want you to go to the bottom of your sheet and figure out where your height gets to the largest value. Mine gets to 11 centimeters. Find your largest value. It should be right around the very end, but perhaps if you overselected it might be a little off. But find that last value and select it. And then type a minus. So you will see what I just did there. I selected the 42nd entry for H. Mine's 0.11, and I put a minus. Do not hit enter yet. We're still not quite done. We're almost there, but we're not quite done with this cell. So find your largest H value and do that value minus D2. And now I'm still up here in the formula. What I need you to do real quick is add a $ in front of the D and a $ in front of the 42, or whichever cell that is. Don't touch the red one, but this blue one needs to have a $ right there and a $ right there. Please very carefully make sure that you have the exact same stuff written into this formula. And I'm going to hit enter. And I'm going to drag and drop it through. That first one, you need to grab the little tiny square and drag it through the whole way. Or you can just double click the little square. Thank you to Nader for helping out. Very helpful day to have in LA. And now let's double check our sanity. Kinetic energy still starts at 0 and goes up. Spring energy starts at 0 and goes up. Gravitational energy starts at a big number and goes down. Make sure that that's what you have shown. Okay? We go on to total? Previously, we talked about this. Our total energy should just be whatever our initial gravitational energy is. So you could make a reference to that in Excel, or for right now, I'm just going to go ahead. I'm going to look at that number, 1.14, and I'm going to put it there. 1.14. Whatever your number is there, right next to it, just put it in there. And then fill it in the whole way. That's what your total energy should be at every step of the way, every tick of our clock. It should just be that total. Good, good, good. We're real close now. Our thermal energy, we will need an equal sign. And this formula is pretty easy. We need to make a reference to the total, minus the kinetic, minus the spring, minus the gravitational. So we will do E equals cell I2 minus cell H2 minus cell G2 minus cell F2. That's what your formula should look like for the thermal energy. It takes this one, minus this one, minus this one, minus this one. And we hit enter. And then we drag and drop it through. And your thermal energy, little bit of a sanity check, should start at 0 and get bigger over time. Little bit. Now, if you have a negative, don't overthink it for a sec. I will help you correct that in a sec. There are some experimental errors that happen, and we'll talk about that in a sec. But first, before we go fix up anything that may have minorly been incorrect, it's time to make that graph. And we've been waiting for the moment of truth. So please go ahead and click column E. You could just click and highlight all of these if you want, or if you're on tablet, you probably want to click column E, hold the shift button, and then click column J to select all of that range of data. We'll go up to insert. We want a scatter plot now. So right here, go to your scatter plot, and I want the one that's a smooth line. I don't want the one that is dots. I want just a smooth line. And now we're real close. I think most of you know on Excel, we've done Excel before in this course. I'm just going to clean mine up a little bit, and then I'll allow you to clean yours up, and Nate and I will rotate around and see if you're getting it. I want to do maybe 3.4 second, no, 3.8 seconds to about 5.3. And once you get your graph, please make it large so that I can come around and check yours. If you get something like this, you have done it successfully correct. Spring energy, gravitational energy, kinetic, thermal, and total. Anybody is going negative for the thermal energies, we'll talk about that in just a sec, but let's just pause. I think 5 out of the 8 groups have the graph roughly correct. There's certain experimental errors that cause this to be a little bit weird, and also depending on how you selected your data and how you ran the experiment, it's very important that we select the right range of data, and you don't quite have the intuition yet for what is good data or when to cut it off yet, but we can talk about that a little bit more at the end. First, let's just take a look at our actual plots that we have here. We have total energy staying constant. We have gravitational energy starting big and going to 0. We have kinetic energy starting at 0, getting up to some point and going back to 0. We have spring energy starting at 0 and going to a maximal value that is less than the total energy, and that difference between the total energy and the spring energy is what value the thermal energy eventually gets up to. This graph is a correct representation of all of the different types of energy. And so, if we take a look at our graph, we'll realize that it wasn't quite right. It started and ended and had the midpoints at the right spot, but the shape of it was actually a little bit different. So, let's do some small course correction. My gravitational energy, I'm going to correct that. And it actually has more of like an S type of shape. So, it might be somewhat flat, go down a lot, and then flatten out at the end. Okay? Let's talk about our kinetic energy. Our kinetic energy was not a perfect parabola. There we go. Our kinetic energy starts flat, goes up, and then flattens out again at the end, so it wasn't quite a perfect parabola. Our spring energy also has an S-like shape. Meaning that it started off a little bit flat, leveled out, sort of like so. And the thermal energy was not linear either. It also had an S-like shape, but it in general was relatively flat. Should be something like that. Now, the only one of these that I might actually expect you to have some intuition about why it's doing this is the thermal energy, actually. Some of these other ones are S-like shapes, and I wouldn't expect students in Physics 210 to have been able to predict that. Maybe if you really, really thought hard about it, you would have been able to guess that. But there's one that I want to highlight, and that's the thermal energy. You'll see that in the beginning, we didn't create very much thermal energy. Maybe it went up just a little bit. And in the end, we really didn't create very much thermal energy. It pretty much stayed roughly where it was. But in the middle, there was a big spike, a big change in our thermal energy. Please turn to your neighbor and quickly speculate on a reason why the thermal energy might change a lot in the middle of the track. Go. I'm hearing some different explanations, some good thoughts. Anybody want to share a speculation on why the thermal energy might change a lot in the middle, Tyler?
That's when it's going the fastest.
That would be the simplest and most intuitive answer. The car is moving the fastest in the middle, and when objects move fast and rub up against each other, they create a lot of heat. So, I can put my hands together and go kind of slow, and I'm not making very much thermal energy. But the faster that I go, it starts to get pretty toasty, right? And so that's what happened right here in the middle. Our car was moving really fast, so our thermal energy jumped up really fast for a short amount of time there. All of the other ones I would not have expected you to be able to guess. This one, maybe you could have speculated and said, I think there will be a big spike in thermal energy because it's moving really fast. In other words, the more friction that we have, the more thermal energy there will be, and there's more friction when objects move faster.